to roll. Thank you. Hello everyone. Thanks for coming today. It's a pleasure to have Dr. Justin Dressel giving my poor presentation or introduction of him yesterday. I'm going to do a better job today. So reading out from his website, proper website. So Justin is Associate Professor of Physics at Chapman University here in both the Schmidt College and Institute for Quantity Studies. He got his PhD in Physics at the University of Rochester under the supervision of Andrew Jordan. And then he worked as a postdoc at Hinken in Wakoshi, in Japan under the advisement of Franco Nori. Also in California Riverside under the supervision of Alexander Korotkov. And he here with us since 2015 as an assistant professor and was awarded tenure in 2019. And he primarily researched in quantum information science, quantum computation, and foundation of quantum physics. And his recent research has revolved around the development of superconducting quantum circuits for quantum computation in collaboration with experimental groups at Google, USC Santa Barbara, MIT, USC, and UC Berkeley. And today he is here to talk about non-Hermitian evolution from continuous monitoring. Justin, floor is all yours. Thank you.
Thank you, Chris. And thank you for all of the IQS organizers for having me speak here. It's a pleasure to speak here in our new building as a member of the IQS community myself. So I want to talk to you today about a whole lot of technical detail on something I've been thinking about for a while. As Chris just pointed out, I've been thinking about superconducting circuits and quantum computation in superconducting circuits for quite some time. And part of what's really interesting about these circuits is that it forces you to really pay attention to what the measurement process really looks like in a physical system. And I'll be detailing kind of how measurement is actually done and how we need to mathematically model that measurement in a lot more detail in these physical systems. So without further ado, here's how my talk is going to look. So first of all, I'm going to assume that not everybody knows what superconducting qubits are. So I'll give you kind of a brief introduction of what those are, what circuit quantum electrodynamics is, which is the main way of describing these things, how we do readout kind of in broad conceptual terms. And then I'll go into a lot more detail on how do we actually mathematically model that readout at various levels of detail. And I'll also highlight why we need various levels of detail and under what circumstances that detail matters. This is work done in collaboration with many people from my team, including Sasha Greenfield, Corey Pantea, Luke Burns, and Dominic Briceño-Colunga. So what are superconducting qubits? In one slide, here's the idea. They're mesoscopic coherence of collective charge motion. So these are circuits, charges moving in circuits. They're micrometer scale. So these are wires at micron size, and we cool it down to millikelvin temperature. The electromagnetic fields of the charge motion in these wires are described by what's called circuit quantum electrodynamics, which is a kind of restricted version of quantum electrodynamics suitable for circuit theory. And harmonic oscillators that we create on chip, the potentials of those can be treated as artificial atoms that we can engineer. And the lowest two levels of these artificial atoms we can then use as a qubit. So something that we can store two distinct levels for informational purposes on. These qubit levels are controlled by microwave field drives, which we couple to these n-harmonic oscillators. And then we measure these qubit levels with dispersive frequency shifts of coupled microwave resonator modes. And then we'll talk a whole lot more about what this means in a second. But kind of as a high-level overview, this is what the architecture looks like. This is how everything works in these kinds of systems. Now, for circuit QED, the simplest way to understand kind of the basics of circuit QED is to just think about canonical quantization as you learn in undergraduate quantum mechanics. So you're usually thinking about position and momentum as canonically conjugate. Well, in these circuits, it turns out that flux and charge are the two canonically conjugate variables that behave analogously to position and momentum. So everything you learn from undergraduate quantum ports over into these circuits very naturally. In particular, You can set up a canonical commutation relation of flux and charge. You can even rescale these things to dimensionless versions of these things. It's you, Chris. And if you can create a circuit, for example, like a harmonic oscillator, which is just an LC circuit, an inductor and a capacitor, then it behaves exactly as you expect a quantum harmonic oscillator to behave. So it has a quadratic potential that yields equally spaced energy levels, discretized energy levels. Now, this is a very easy circuit element to make in such a chip, but it is a very bad qubit for the reason that all the levels are equally spaced in a harmonic oscillator, which means if I try to couple this to some external control, then all of the photons in my external control have the same energy. They're going to send me up and down this ladder of the harmonic oscillator arbitrarily far. I won't be able to isolate a particular subspace of my harmonic oscillator in order to control it like a qubit. It's a very useful circuit element, but it's not yet a qubit. So in order to get something that looks like a qubit in such a system, we have to go a little bit beyond harmonic to an anharmonic type of circuit. So the simplest anharmonic circuit is basically a quantum pendulum. And we get one of these quantum pendulums by introducing a new circuit element called a Josephson junction, which is basically a tunnel barrier where I sandwich two superconductors with a very thin insulating layer. In this case, I would have, say, an aluminum wire, and then I allow it to oxidize and create a little aluminum oxide layer on top of it, which is insulating, and put another aluminum wire on top. If I cool all of that down into millikelvin regime, the aluminum becomes superconducting, the aluminum oxide does not, and then I have a nice little tunnel junction. So that's all a Josephson junction is. What's interesting is that when you look at its energetics, its Hamiltonian has this 1 minus cosine of kind of this flux form. And this 1 minus cosine type potential is precisely the same potential as a pendulum. So it in fact is a quantum pendulum on a chip. The interesting thing about such a Josephson junction is it acts as a nonlinear inductance, which means I can kind of drag and drop it in for a linear inductor. And now I have a nonlinear inductor that adds this anharmonicity to the dynamics of my oscillator. And that allows much more interesting things to happen in the circuit. And these Josephson junctions are used throughout these superconducting circuits as a source of nonlinearity, if you like, for a variety of purposes. But if I just look at the cosine potential that's produced by such a Josephson junction, the first interesting thing you get out of it is that the levels in such a cosine well are no longer evenly spaced because of this anharmonicity. And that means that I can now isolate a pair of levels and say that I'm going to use as my computational subspace for my qubit. I can now address it with a very specific energy gap with like a microwave tone, for example, and I'm not going to risk causing transitions between other level pairs just because I've now isolated a specific energy gap because of this anharmonicity. Now, this leads very naturally to the most kind of common qubit that are used in these superconducting circuits, which is called the transmon. So a transmon is literally just taking your LC oscillator, taking out your linear inductor, and just dropping in a Josephson junction as a nonlinear inductor. So it replaces your kind of parabolic potential with this 1 minus cosine potential. You choose your parameters carefully to make this shunt capacitor very large. And what the shunt capacitor does is that it protects the system from charge fluctuations. So you basically get shielding from charge fluctuations. And this is why this transmon has been such a robust piece of hardware that's now used by many, many companies. That the charge protection and the simplicity of the circuit kind of combine to make this a very nice qubit. But in detail, your potential looks something like this. It's this almost parabolic potential at the base, which then bends away from the parabola as you go further up the cosine. There's roughly 7 levels in such a transmon potential total, but we isolate the bottom 2 as your qubit subspace. For sake of numbers, the main qubit energy gap is something around 4 to 7 gigahertz. So it's in the microwave regime. And the N-harmonicity, meaning the detuning of the next level gap away from the bottom level gap, is around the 100 to 300 megahertz, just to put some numbers on it. This means you can have a very nice effective Hamiltonian in the eigenenergy basis, where we can keep at least the bottom few levels, and then we can start thinking about it as an actual qubit. Now, what's nice about this is that this effectively acts like an artificial atom, where I have level structure, just like an atomic, or just like an atom, but I can now engineer what these levels look like in a way that I can't engineer our actual atoms. And even more interestingly, because I'm engineering the coupling to these circuits, I can engineer the coupling to the atom in a way that actual atoms, we can't usually access that kind of coupling. In particular, we can get ultra strong and deep strong coupling regimes with these engineered chips that are just not attainable with normal atom couplings. So it lets us explore regimes of different physics, especially quantum physics, that are very difficult to explore with typical atoms. So there's a lot of just interesting physics you can do with these systems because we can engineer them.
What does deep strong mean?
Deep strong means even stronger than ultra strong. I didn't invent this terminology. It's actually a common quantum optics terminology. I don't know the origin of why they called it deep strong. I should, but I don't. The other thing I'll note here is that the coupling to these kinds of systems, because it's all on chip, I can have a waveguide right next to my artificial atom, and all of the emissions from my atoms, you imagine like an atom like emits a photon when energy decays. Normally, like an actual atom will emit it in free space in 3 dimensions. Well, on these chips, it actually just emits the energy from that energy transition directly into the waveguide. And so I can collect with very high efficiency all of the emissions of the atom and then process those emissions. And this is something that's very difficult to do with actual atoms and actual quantum optical systems, but it's very easy to do with these circuit systems. And that feature is what's enabled us to be much more precise about what the measurement process is looking like, is this high collection efficiency. Okay, so I kind of toed around the issue, so let's confront the main issue here. So how do we measure such a superconducting qubit? The problem is that this is a chip, it's a little circuit on a chip inside a fridge. I've cooled this fridge near to absolute zero, and now I want to ask, what is the energy eigenstate of this particular harmonic circuit in this chip? But I also don't want to cause any unwanted changes to the energy states while I'm trying to learn what those energy states are. So the question is, how can I do this? I can't just go look at my chip and say, what energy are you? Just work that way. I need to engineer some sort of interaction and figure out how to pull out that information. So the way this is done, and basically all superconducting qubit systems, is that we indirectly peek at this energy by sending in a microwave tone. Basically, we have a signal generator on the outside of the lab somewhere, send it down a coax cable that goes inside our fridge, and then that microwave tone will couple to a resonator, a microwave resonator, that is itself coupled to the qubit. And the idea is that if we detune the microwave resonator very strongly from the qubit, then we suppress energy transitions between the qubit and the resonator, which means we protect the energy of the qubit, but we're still dispersively coupled, which means that the frequency of the microwave will depend on what the state of my qubit is. And so if I can learn what the frequency changes of the microwave are, microwave resonator, then I will learn the corresponding kind of qubit state as well. And so I can peek at the qubit energy with this dispersive coupling, and by looking at the frequency shift of the field that goes in, interacts with the resonator, that like picks up the phase shift based on how the resonator frequency has been shifted. That field comes back out of the fridge, and then I can look at that field and I have to compare it to something. So I have to have a reference to say how much has the frequency shifted in that microwave, and then completing that comparison, I can then look at this like microwave tone. Now, this sort of measurement where we're trying to not disturb the energy eigenstates, in the quantum literature, this is called a quantum non-demolition measurement, or QND measurement. But what's interesting about this kind of setup is that there's an inherent time dependence to this. I'm sending in a microwave tone continuously in time. It's interacting with the system continuously in time. It's coming back out of the system continuously in time. And then I'm collecting a time-dependent signal. And then per unit time, as I collect it, I have to infer something about what the qubit is doing. So intrinsically, what I'm doing here is a time-dependent, time-continuous measurement process. Now, what this means is that I have to parse the signal of what I get out and infer information from it. So the way this works, like the comparison that I do between the reflected tone and my original tone, this is called a homodyne measurement or a heterodyne measurement, depending on how I do this. And what I'll collect at the end of the day after amplifying it, doing this heterodyne measurement and so forth, is going to be an intrinsically noisy voltage signal that has time-dependent voltage. This signal will be noisy due to the intrinsic vacuum noise of the signal generator. So we actually have like quantum limited vacuum noise coming in here. And what we're going to get at the end of the day is some voltage that looks something like this. So there's going to be just incredibly noisy voltage coming out that we then need to filter in some way in order to get the information that we care about the qubit. So this filtering process requires kind of two steps. There's going to be a classical signal filtering process of just how do we deal with this noise in order to get out something sensible from the noise. And then there's a quantum state filtering process, which is how do we infer what this means about how the quantum state must have been changing based on what we see from this noise on our oscilloscope. Now, it turns out that we only really need two basic quantum mechanical rules in order to determine how this works. The first is Bayes' rule from probability theory, which basically says that when I see some random signal, then I should be able to update the information that I have about other probability estimates based on how I know the likelihoods of that random signal should be. The second thing is Born's rule from quantum mechanics, which kind of embeds probabilities directly into the quantum theory itself. And this means that if I need to update probabilities with Bayes' rule, I have to update those probabilities inside the quantum state, which then forces me to update the quantum state. And what I get out of the combination of these two things is actually a partial collapse mechanism of the quantum state directly from Bayes' rule through Born's rule. So at the very simplest level of understanding this kind of readout mechanism, that's what's going on. Now, of course, there's more details here. I have to amplify these signals in order to be able to see them. So there's several ways we can amplify them. And it turns out that the mechanism of amplification is not so innocent. How we choose to amplify it will actually affect what information is in the signal, which therefore affects what it's going to do to my quantum state. So I'll briefly mention this. We won't go too deeply into this, but there are two main ways to amplify. One is called a phase sensitive amplifier, like just some parametric amplifier will do this. And with a phase sensitive amplifier, what you effectively do is you squeeze the microwave tone along a particular quadrature, and then you'll measure along that squeezed quadrature. And what this will do is if you have two different steady states in the resonator that pop up because of your two different qubit states, I can now squeeze along one quadrature and kind of maximize the information of the separation of those two qubit states, and then just measure along that quadrature, and I'll get a very nice, clean, single, real signal that has all the information about my qubit states. But I also have the freedom in such a phase-sensitive measurement to choose a different axis of squeezing. So if I squeeze along a different axis, for example, I can now squish these two blobs together. I now erase all of the information about the qubit states that I had originally. And then if I measure along this axis, I now get no contrast about the qubit, which means that my readout that I get actually has zero information about my qubit states. It's telling me about something else. If I do that, so in these squeezing cases, this means I can choose kind of two orthogonal cases. One, I'm going to maximize the information about the qubit. So I can think about this as an informational quadrature that I measure. The other is I erase all the information about the qubit. And the thing that I learn about is actually the photon number fluctuations in the resonator. So my signal like the information in my signal will depend on how I process the output field after it leaves the resonator. Now, the other way that we can amplify these systems is what's called phase preserving amplification. And this is kind of a uniform amplification where I just kind of blow up this whole IQ plane. And then I'm going to measure two signals. So I actually get two quadrature signals, and this is equivalent to a single complex signal. And then I'm going to have information both about both of these things simultaneously. The penalty for such a phase preserving amplification is I get a net efficiency factor of 0.5 because I've split my signal into two different quadratures and I'm measuring them both simultaneously. Heisenberg's uncertainty principle says I can only do this up to some finite precision. The best precision I can do it with has this extra factor of 0.5 precision. So I can do it in either way. And actually there's a lot of interesting stuff about this, because you'll notice that I can choose how I amplify this thing kind of after the field has already interacted with the qubit. The field has already left the qubit. I can actually make choices about which squeezing quadrature I do and so forth long after. So this is a classic kind of quantum delayed choice effect where I can choose long after the interaction how I measure the system, and that will have different effects on the system itself based on which choice I make. There's a lot of interesting kind of foundational stuff hidden in this process. But let's go back to the simple case. So suppose I do just a phase sensitive measurement, squeeze it along the informational axis for simplicity. So we're focusing on the qubit measurement here. Now, what I can do is turn up the gain. So I put a very strong microwave tone in here. What this does is it creates kind of a big separation between my two different steady states in the resonator, because I have now a stronger pump. And this means I get two well-separated histograms in the homodyne measurement case, which means that when I look at my voltage trace with just very simple classical filtering, I will see two very clearly separated qubit state dependent means. And then I can just literally track quite easily, oh, my qubit state was in 0, it jumped to 1, jumped back to 0, jumped back to 1, and I can actually see those quantum jumps directly in the signal. This is known as a strong continuous measurement regime, where I can actually see the resolved quantum jumps between the eigenstates. And the reason this is happening is because the measurement is strong enough that we get the quantum Zeno effect that pins the qubit state to the eigenstates of the measurement up to very rapid jumps between those eigenstates. So I can see this regime. But if I turn down the pump, doing nothing else, then I'm going to get less information per unit time, because now these steady state blobs are going to kind of overlap much more in the resonator, which means I don't have very distinct what are called pointer states in my resonator that are conditioned on the qubit states. And now my histograms, when I do my homodyne type readout, are going to be strongly overlapping, which means that when I see some random voltage, a particular random voltage here could have come from either one of these histograms, but there's a slight difference in likelihood about which histogram it came from. That difference in likelihood, according to Bayes' rule, gives me a way of updating which qubit state was more likely than the other one. And so per unit time, I can now just track based on my histogram here and Bayes' rule, okay, which signal did I see? How does that affect my likelihoods of being in qubit 0 or qubit 1? If I have some quantum state of my qubit that has these probabilities built into it via the Born rule, so I just apply Bayes' rule and update my probabilities of the qubit state. This causes a partial collapse of my qubit that then conforms to the measurement. This is the simplest way to deal with measurement in such a system. And this works great, provided that I can kind of ignore most of my actual physical setup here and just say these are stable histograms. As long as these histograms are at steady state, these histograms aren't changing, I can just use this very simple Bayes rule prescription and I'm done. I can track the qubit state and get a whole lot of information about what's going on. And this works very, very well. But if I want to actually predict kind of what are these histograms, for example, then I have to go a little bit deeper into the theory. So one approach is to just in the lab say empirically, all I need to do is just measure these histograms. That's easy enough to do. Put my system at steady state, see what these histograms look like for different definite preparations of 0 and 1. Then I have everything I need. Once I have the histograms, I just use Bayes' rule. I don't need to know why those histograms are there. I just need to know there are stable histograms. I can apply my measurement. But if I want to predict what these histograms are and say, okay, let me have a better understanding of why we get these histograms, then I have to go a little bit deeper. And there's a very nice approach due to Sasha Korotkov for a few years back that works at steady state. So again, as long as I'm thinking about my system at steady state, then I can use this and it works extremely well. But what's happening here is I can imagine that I'm pumping my readout system with some coherent tone. So when I apply a classical microwave pump, this is basically like sending in a coherent state, quantum mechanically, of some particular microwave state. That input coherent state then is driving my resonator, which is attached to the qubit. And after I've reached some steady state of the resonator, because I have some input pump, and then it's leaking out, so I get a competition of rates, which yields a steady state, I can find what the two coherent steady states are of the resonator. And I'm going to get two different coherent steady states because I get qubit-specific frequencies in the resonator, and that affects the steady state. So I can actually just calculate what are the two classical coherent states as steady states that I expect to be in the resonator when I pump it with a particular coherent state. So once I've achieved the steady state, then what I can do is say, what's happening is basically like a beam splitter interaction. Like I have a pump coming in, it's going to have some interface here, and I'm going to scatter off this interface. And I can treat it as a scattering problem where I scatter my input, and then it's going to leak out some of what's inside the resonator. And in the output, then I'm going to get the result of this scattering. So I get some output that is reflected input plus whatever came through this interface from the inside. Very nice scattering problem. And this means that per unit time, I can actually write down what this scattering matrix should look like. I know that if there's some rate kappa at which things are leaking out of the resonator, then there's a probability of kappa dt that I get something leaked out of the resonator, which means the probability amplitude of it leaking out is root kappa dt. So I just multiply whatever the coherent state is by root kappa dt. That is the amount of the coherent state that leaks out into the transmission line. Very simple. Now the question is, what do I mean by that? Well, I have to say, well, that scattering process takes some time. So actually what I'm talking about is some segment of the transmission line that this coherent state leaks out into. So I have to postulate there's some width, some dx in my transmission line where I get this scattering relation, and I get that segment of the transmission line now has this kind of leaked coherent state in it. And then once it's in the transmission line, it then proceeds down the transmission line and just kind of propagates. And what this is going to do per unit time then is I'm going to get a kind of a box built up from the scattering process. And this box then kind of goes down my transmission line, and another box gets built up. And then both boxes go down my transmission line, and then another box gets built up. And it's kind of like building a train, and the train just continues down the tracks of this transmission line up until when I measure my transmission line. So those segments of the transmission line will then get measured later on. Now, if you're paying attention here, what this means is that as this measurement process proceeds, I'm getting these kind of boxes built up one after the other. And if I start looking at what does the total quantum state look like, I have something that looks like the following. I can start with whatever superposition of my qubit state I want. I'm going to get adiabatically built up my resonator steady states, alpha 0 and alpha 1, that are now entangled with my qubit states. Now, after each delta t, I'm going to get a piece of the transmission line that is now entangled with whatever the coherent state was attached to that qubit state. And then I'm going to get another box, and then another box, and then another box. So what this means is that for each delta t, I'm kind of building up extra Hilbert space tensor product factors on this state and getting a bigger and bigger and bigger and bigger entangled state as I go. And the longer my transmission line is, the longer these boxes persist before I go measure them at the end, the bigger and bigger and bigger this entangled state gets. Now, what this means is that the entanglement in this entangled state is storing a memory. It's storing the memory of all the past box times of interactions that we had, and what the coherent state was doing inside the resonator at that past time. If I'm at steady state, that time dependence of that memory doesn't matter very much because it's all the same. You can kind of start thinking ahead and say, oh, what if I'm not at steady state? Now, this memory is going to matter a lot, because if something in the resonator is changing in time, then what you expect is that the record of what the past history of what was going on in the resonator will now be leaked into this transmission line. We'll store this whole past history in the transmission line as this like sequence of boxes. Yep.
So what would be the next term, for instance, for following C0? Just because I was wondering if just like it's memory or is more like redundant information stored across the.
It's memory because these are independent Hilbert space factors, which means each of them is independent. It commutes with the other factors and is measured separately. This is very important because when these boxes reach the end of the transmission line, then I'm going to do some homodyne measurement on that box. And each box is going to give me some delta T of information that I see that then becomes a definite signal on my oscilloscope. But I measure box, 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 and I get now a sequence of measurement results because I'm measuring each of these independent pieces of the transmission line, one after the other. Does that make sense?
Yeah.
So it's really important. It is an actual memory because these are truly independent. They're only redundant in the case that we're in steady state, in which case you're entirely right that all of these look identical at steady state, but when I measure them, now I get stochasticity appearing because the measurement results can be random. So even though the states in each transmission line look identical in the steady state, the fluctuations that I see are still there because of the randomness of the measurement itself. Does that make sense?
Yeah.
Justin, in this case, you pay penalty, you are increasing the time, right? To increase the sensitivity of measurement.
Yeah, this I haven't gotten to. What you end up doing is if you
Yeah.
integrate over a long time, then you can get
Why
more
I'm asking?
information.
Because in classical, during the classical, at classical measurement, you also can increase that and it will go like square root of time.
Yeah.
Would you have square root of time here eventually or not?
Yeah, I think so. And I think basically this square root of time you see here ends up being the same square root of time. But yeah, as you integrate it over some duration, then you're going to get more and more information out of your signal. And so you're going to get a stronger and stronger measurement. And in fact, at steady state, I go back to here, for example, another way to get such a strong continuous measurement is just to widen your time bin. So what actually happens here is that this signal, even though it looks like it's continuous in time, there's actually a bandwidth to the detector that has some finite delta T. And depending on the integration time that I put on my detector, then I can kind of sculpt what these histograms look like. So if I integrate over some delta T that's longer, I'm going to get more separated histogram like this, which is exactly what you're talking about. If I integrate for shorter, then I'm going to get a more overlapped histogram like
General
this.
working in both quantum and classical.
Yep, so same thing applies. The difference is in steady state, I can do this because I can integrate arbitrarily.
Yeah.
These states don't really change. But what I'm doing in that
Yeah,
case is I'm
yeah.
actually like collapsing a bunch of sequences of this transmission line and then classically integrating the resulting signal. And it turns out that's basically the same as if I just collapsed onto a bigger block in my transmission line. But it's highly non-trivial. This is true.
Is it possible to send over information through this kind of?
I mean, the qubit is sending information.
Yeah, but in a kind of in a secure way, because if some eavesdropper try to identify what's happening, cutting the line in the middle of it, this person is not going to get like the whole information. Although if you are at the end of this setup, you're going to get like the entire information of the thing. So it's a way to transmit securely, to securely transmit information.
I suspect all the usual QKD type protocols you can apply to this, because each box you can just think of as a separate transmission, right? And so whatever you can say about this particular state or whatever measurements you can perform on that particular state, I think will be the same. It's like in a QKD type setup.
Mhm.
I don't think there's anything special about this particular state as far as that kind of information security. But I think you could analyze this in this boxed-based way as just kind of a sequence of shots in the usual kind of Alice Bob communication setup. So rather than sending a qubit back and forth, they're sending a chunk of a coherent state.
Yeah.
And probably because it's a coherent state, you don't get any security benefits. But if you were to prepare something that wasn't a coherent state here, then maybe. I haven't thought about it in too much detail, but it should just be the equivalent to just a sequence of shots of something.
Sorry, went over this, but I'm having a little trouble reading this notation. Why is it 2dt? Where is the factor of 2 coming from?
Oh, so this is just saying that after 2dt, what happens is I started with my qubit. The first dt, I built up my coherent state in the resonator. Second dt, one like chunk of this leaked out in the transmission line. And so now I have my next time in the resonator. So what's happening is that every time in the transmission line is kind of in the past compared to what was currently in the resonator, because it leaks into the transmission line and then just propagates unchanged. So if something changes in the resonator, then that's not going to change what's already propagating. Which means that as I keep advancing time, in principle, what's going on in my resonator can change. But what's in the transmission line is a past record, a past memory of what was previously going on in the resonator.
Further down the transmission line?
Yeah.
So if you did 3dt, then you would have 3dt in the alphas and 2dt in the.
Yeah, it would be 3, 2, 1. And 4, 3, 2, 1, etc. So the point is that I'm building up this kind of tail, is the word that Sasha Krotkov likes, building up a tail history here. But what's interesting from a math perspective is that I'm just tacking on Hilbert space tensor products, which means that I need sort of to envision, before I can even think about this problem mathematically, an extremely large tensor product Hilbert space, where I have as many boxes as I need to model a transmission line, kind of before I even get started. And each of those boxes depends on this notion of dx and dt. And so how I define my tensor product structure and my Hilbert space structure actually kind of needs to preemptively know what I'm going to be doing. And then there's a question here of, well, what sets this box? What actually physically sets what this box is? Well, it turns out the detector sets what my box is. The modes that I'm going to be absorbing in my detector will actually tell me what is the correct Hilbert space factor I need here. And then that is the thing that I'm going to be projecting onto as a state. So there's a lot of kind of subtlety even in this model. It's a very nice model, but there are questions here of how does nature know what Hilbert space structure to set up? It seems like it needs to know the future about what I'm going to detect in order to even set up what the problem is. So this caused a lot of debates over the years about like, how is a better way to think about that? But there are a few more things here before I move on, just to highlight. One is that if I trace out this transmission line and just look at the reduced qubit resonator state, then indeed I'm going to get the effective ensemble dephasing, ensemble decoherence due to measurement of my joint qubit resonator state. And we'll see in a second that this formulation lets us calculate that very easily because these are all coherent states. The second thing to note is that the actual measurement, what it's doing is that it collapses each of these factors of the transmission line once it reaches the end of the transmission line. So this just proceeds as a box, goes all the way down to my detector, that gets amplified, that gets compared with another thing, and then I measure it. And so I basically post-select on a particular measured outcome of one of these boxes at a particular unit of time delta t, and that's my measurement result that I see on my oscilloscope. And so I just see a sequence of boxes coming in from the perspective of the detector. Each box that comes in, I collapse it to a particular result. Next box comes in, I collapse that to a particular result. Next box comes in, I collapse that. So I can apply just, again, undergraduate quantum mechanics. Every measurement is just collapsing one of these state factors in this enormous entangled state that I've generated. So as a quick kind of schematic of how this actually looks, I can calculate this fairly precisely. I say, okay, classically, here's my coherent state amplitude. There's going to be a dispersive shift that depends on the qubit state, either up or down by some chi. These amplitudes leak out of the resonator with some rate kappa over 2. There's some like constant pump, which I'm going to call epsilon, which is my input coherent state. If I solve for the steady states of this resonator equation, I get these two steady states, which are differing only by this kind of dispersive factor in the denominator here. These actually have the same n bar, the same average photon number as the complex square of those coherent states. So all this is very well defined. Then I say, okay, let me just look at the reduced qubit resonator state. So take that big entangled state and basically trace out the transmission line. What you find is that each piece of the transmission line gives us a factor of this in the off-diagonal elements of my reduced density matrix. So I get an overlap between my coherent state alpha 0 and alpha 1 up to these like leakage factors kappa d, root kappa dt. If I compute what is this overlap factor, I can write it in this way where I see a natural kind of measurement rate pop out and a natural like phase frequency pop out. This measurement rate has this form. If we evaluate it, it's this. This is precisely the measurement rate that is well known in circuit QED. So it computes this very easily. And we get for free an extra frequency shift that happens, which is called the AC Stark shift. This means that as I populate the resonator, the added photon number in the resonator changes the qubit frequency as well, because there's a symmetric kind of back action of the cuff. So all this pops out. It's extremely easy to calculate in this coherent state model. So it's a very effective model, very successful model when we have steady state. I can keep going with this and say, okay, well, what happens if we actually measure my transmission line? This was the ensemble average effect. If I just trace over it and don't look at how I measure it. But if I actually measure it, let me just project onto a particular, say, quadrature. So this would be a phase-sensitive approach. Let's project onto a quadrature. What happens with this big entangled state is now I'm projecting one of these pieces in the transmission line onto a particular quadrature value, I theta. And now you see I get two different overlap factors because I have two different coherent states here. Now I can rewrite this in this kind of suggestive form here, where I just lump all of the effect of these overlap factors into some qubit only measurement operator M. When I look at what these overlap factors are, then I can use this nice undergraduate quantum mechanics identity of how to overlap kind of a X, like a position eigenstate with a coherent state. And we get some expression like this. I can work that out, look at what this implies about the qubit POVM coming from this M, and we find that indeed it evaluates exactly the Gaussian POVM, where we get some signal R after rescaling the actually measured signal to something that is more finely tuned to the qubit. We get this signal R that has a qubit state dependent mean, and then there's a measurement rate that sets the width of this Gaussian. So everything pops out of this exactly as we expect and conforms to what we see in the histograms in the lab. So this is very nice. Now we can go even more specifically and say, okay, that's what the POVM looks like. That gives us the probability distribution for what we see. What does the measurement operator look like? So it looks like this. We just get these overlap factors times these qubit state projectors. Very intuitive form. When we evaluate this thing out, what we're going to get is kind of a factor that cancels with state renormalization. There's going to be some unitary that handles the AC Stark shift type terms. And then there's a measurement term, which has this nice exponential form in terms of whatever our quadrature angle is, theta. So all this pops out, we get a very nice simple result. And this result agrees with all the effective qubit measurement modeling that we've used in the past. So this is fantastic. Very easy to work with this model. However, so what are the takeaways here? So this is a coherent state scattering model. It works extremely well, predicts experiment well. It depends on this transmission line boxcar width, this kind of mysterious dx and this choice of dt. That's set by the detector time resolution, which is kind of a weird thing to do. Each boxcar is an independent Hilbert space factor, as I mentioned, and each boxcar must be a commuting bosonic mode because I say there's a coherent state in it. I can only have a coherent state in this if it's a bosonic mode. So I know implicitly I'm talking about bosonic boxcars. Now, the limitations of this is that I am at steady state. So no transient evolution can work with this kind of model unless I make everything coherent states at all times. It's assuming an adiabatic qubit evolution. So on the time scale of these boxcars, my qubit basically hasn't changed. That allows me to do this kind of decomposition so easily. It assumes these conditional coherent states, and each conditional state on the qubit state is actually a coherent state. There could be more exotic resonator states in principle, in which case this would kind of fail. And this is really good for getting these analytic formulas that I just showed, but it's not very good for numerical simulation of the resonator. Like, what is the actual resonator doing? As long as I only care about the qubit, this is a good model, but it's not good for the resonator. So there's a question of like, can we do better than this? Well, a few years back with Irfan Siddiqui's group, we tried using machine learning to kind of go a little bit further than this kind of model. And we found that we could use machine learning. And in fact, as we like ramped up our qubit evolution to break this adiabaticity assumption about qubit, then a machine learning model actually worked way better than this simple steady state model. I won't get too far into the details of this machine learning approach, but one of the takeaways was that what ends up happening when you go outside of the steady state approach is that if I start rotating my qubit, say at some Rabi frequency very rapidly while I'm measuring, the effective axis of the measurement actually gets tilted by some amount due to this interaction with how the evolution of the coherent state and the resonator is actually proceeding. And so any actual like good model of the measurement should reproduce this kind of tilt, this effective tilt when I ramp up the speed of my qubit evolution. So this means that there should be a way to do better than this. But to do better than this, kind of you have to increase the complication by quite a lot, it turns out. So I went back to the drawing board and say, okay, let's do the actual circuit QED of this and see how do we actually describe this correctly. So to do the actual circuit QED, I need to actually bring in the transmission line seriously. So what is a transmission line? Transmission line is a quantum field, meaning that for every point on the transmission line, I actually have a quantum field at that point, a local quantum field, and I can set up sort of some flux and charge fields that are delta correlated at that point. If I write the Hamiltonian for my whole transmission line, it'll look something like this, which can be decomposed into left and right moving parts down this transmission line. It can also be decomposed into global harmonic modes, which is the typical way people quantize field theories, is by looking at over the entire transmission line. These are the harmonic kind of oscillatory modes that are supported on the entirety of the transmission line. The local traveling waves right and left in the transmission line have this kind of form with this kind of funny commutator that involves this derivative of a delta function in it, if you haven't seen that before. And the global harmonic modes can be written in terms of these traveling modes, so I can get both right and left moving harmonic modes in this kind of Fourier transform-esque way, but with a root frequency in there. And then after I built this up, then I get a bosonic structure for my harmonic modes. Now, of course, you can say, oh, that's great. I have bosons. I have harmonic modes. That must be what I'm measuring. That's clearly not what I'm measuring, because these are global over the entire transmission line. I'm not measuring the whole transmission line. I'm measuring 1 delta t of my transmission line at a time, which cannot be these global bosonic modes. So the question is, what am I measuring? Well, let's keep going before answering this question. So how does this transmission line talk to my resonator? Well, it turns out the coupling Hamiltonian between the transmission line and the resonator is a flux coupling to the resonator times the current at the transmission line at the boundary of the transmission line. If you write all that out, it looks like this. I can write it out in terms of the global modes here, and then I can rewrite those in terms of some input-output modes that I define in this way. And now these input-output modes, I can now kind of center around a particular drive frequency. And this trick is that as long as I look at a very narrow band signal around some particular drive frequency, then these input-output modes will look approximately white, like a delta correlated around that narrow band frequency near my resonator frequency. When I do that, I can now see what this kappa is going to be, this decay rate into the resonator in this narrow band sense around my signal. It's going to be my frequency of my resonator times the ratio of the impedances of my resonator and the transmission line, which is a very kind of intuitive form of this capo. Now, what's interesting with this whole approach is that in order for this to work out, I also have to apply a constraint. It's not just a simple Hamiltonian system, it's a Hamiltonian system plus a constraint. And that constraint is the boundary condition at the interface between my transmission line and my resonator. That constraint basically boils down to the equivalence of the fluxes at the end of my transmission line. And then if I take a narrow band assumption and I look at some drive frequency that's coming in at the transmission line, then I can factor out kind of this overall drive amplitude and rewrite this same boundary condition as what's usually called an input-output relation in literature. And this would be the RWA input-output relation, which is basically just saying at the boundary, what's leaking out of my resonator has to be related to the sum of the input-output fields at the boundary of the resonator. So a very intuitive thing. This is great because now I can say, well, my effective Hamiltonian, after all of this rigmarole and applying these boundary conditions, I can write in this way in terms of these input-output fields, which means I can use the Heisenberg picture, find what the actual evolution of the resonator is, and I get this. And then if I apply my boundary condition to my Heisenberg equation, I get this equation, which is the quantum Langevin equation that depends on now kind of this vacuum noise of my input field. So here's where I can say my input field is some coherent state plus some intrinsic vacuum noise that's approximately delta correlated in some narrow band right around my detector, my drive frequency. And I get this very nice quantum Langevin equation. And from the Langevin equation, once I solve this thing, then I can know what the reflected field is going to look like because it just depends on the solution of A. And again, this vacuum fluctuation. Now, if all I cared about were ensemble average statistics, this is a great approach. But the problem is this doesn't allow me to build in measurement because in the Heisenberg picture, it's not clear how do I condition on particular observed results in my measurement. So I still have to go a little bit further than this in order to get back something that I can recognize as a conditioned measurement. So to do that, I have to take seriously, like, what am I actually measuring at my detector? In some sense, what this is allowing me to do is say, this is the thing that infinitesimally per unit time is traveling down my transmission line, but I can't measure it infinitesimally at time. I'm going to wait, and what my detector is going to do is integrate that output signal with some delta t. So the thing that my detector actually observes will be an integral of my output field over some compact wavelet mode. And the simplest wavelet mode is just a boxcar wavelet. I just literally integrate for some delta t. And if I normalize this wavelet node just right, then as long as A does not change that appreciably on this scale delta t, this approximately looks like this in terms of an input mode, which is just the integral of my input field over this same delta t. When I do this integral of a compact wavelet mode, then I discover that these input-output integrated wavelet modes are bosonic. So these are the bosonic modes that we need to appear. They are determined by the detector. So what I do at the detector actually tells me which bosonic mode I'm going to be coupling to. And now I have a correct bosonic commutator. I can build up coherent states. I can now kind of recover what's going on.
With which accuracy? With which accuracy?
With which accuracy? So it depends what you mean by that. So here I'm using a small delta t in order to make this approximation, but I can also integrate over many, many, many boxes as well. And then I can get.
So you have estimate for
Yeah.
accuracy.
Yeah. And I think I can answer your question by saying we can make it as accurate as we want. But the approximations here, I'm assuming small delta t for simplicity, but then I can just join a bunch of them together. But this is interesting because there's an arbitrariness to how big I make this delta t that I'm setting at the detector. That's actually set by the bandwidth of the detector. Because my detector itself is going to kind of integrate with some time resolution, but I can't get arbitrarily fine in time resolution. Now, what this means is that my total propagator, again, coming back to this was my Hamiltonian here, that Hamiltonian will lead to a propagator. My total propagator, when I integrate it over just a single boxcar of my transmission line, that will yield this form in terms of the bosonic modes in my input-output line. And interestingly, there's now a root kappa delta t that appears here in the effective propagator. So usually we think of a Hamiltonian having a delta t, But here we get an effective root delta T that appears here because I've now rewritten in terms of the actual measured bosonic modes rather than kind of the instantaneous non-bosonic modes of the transmission line. Now, what this means is that I can now apply my input-output relation at the level of my bosonic operators to this effective propagator, and it will reformulate this propagator entirely in terms of my output field, like so. And this is nice because if you look at this, now the effective interaction between my resonator and my output field has a form of a displacement coupling, which is very intuitive, that I'm kind of displacing, I'm kind of removing field from my resonator and adding field to my output mode. It's very intuitive that it should be a displacement coupling of this type, of this sort. But I have to be very careful. This constraint, because it's a constraint, means that I can't both think about the input and the output mode separately. I have to link them somehow. So what's actually happening in terms of boundary conditions is that I start with an input coherent state in my input mode, but I can interpret this as a displacement operator on the vacuum that gives me a generated input coherent state. Then I apply my constraint, my input-output condition, to rewrite this displacement operator in terms of my resonator and my output field. This gives me an effective pre-selection of my output field, which is opposite in sign to the pre-selection of my input field, and an additional displacement on my resonator, which is equivalent to the drive displacement. So this is where the drive Hamiltonian for the resonator actually comes from, is that it's coming from the input pre-selection on the transmissions line. So again, very intuitive that it works this way, but in order for it to work this way, I have to actually apply this constraint while thinking about quantum fields and using the fact that the vacuum is the same vacuum for all bosonic modes that I could possibly define. Then it works out.
Is that true? Is that appropriate assumption?
Yeah.
That vacuum is the same.
Yeah, and this is what's very interesting, is that I have to make this assumption, and it is correct. But normally, if I have non-relativistic quantum in my head, I'm not thinking about that. But it turns out I really need to pay attention to the role of this vacuum very carefully here, because I'm working with a constrained system. If I try to do things in an ad hoc way and I don't obey this constraint properly, then I get problems. Now, this means I can get back to my steady state picture by, again, taking my propagator, taking my now kind of reinterpretation of my input boundary condition. And now I can say, okay, what a measurement is doing is that I'm post-selecting a particular state, say I theta, on my output transmission line mode. And this gives me an effective cross operator in the usual form. So I'm going to get this input boundary condition, my propagator for each delta t, and then my output post-selection, just like I expect a cross operator to look. When I plug in all these things, it gets this very long form, like so, in terms of just an output pre-selection and an output post-selection. So now everything is self-consistent in the same Hilbert space. Everything's fine. And what you'll see here is that when I rewrite this, I'm going to get an effective Hamiltonian evolution for my resonator, which now includes the coupling to my qubit and the drive, the effective drive Hamiltonian that comes from this term. But then I get this overlap factor left over, and this is precisely the overlap factor that appears in the Korotkov steady state coherent state model. And so what this means is that after you kind of subtracted out some of these input pumps and so forth, which makes it equivalent, we recover this nice boxcar model of steady coherent states out of it. So it does in fact follow from this kind of more rigorously, but now we can see like what assumptions at which stages we had to make in order to get that effective model. And that lets us go further than that. So now we can say, let's loosen the assumptions of steady state. Let's allow arbitrary states in the resonator. What do we need to do? Well, we now can go back to this cross operator and say, okay, let's just evaluate this differently. So in this case, let's look at a phase preserving measurement for simplicity, which means now I don't squeeze it. I have two quadrature signals, which gives me a complex result R. And what I'm going to do here is post-select on a particular output state that depends on some R, pre-select on the input in the same way, and then I can rewrite this thing in a different way. So now I'm no longer assuming that my resonator is in a coherent state, but I get this kind of overlap factor times the effective Hamiltonian evolution of the resonator. And this overlap factor here, after I kind of symmetrically remove this similar displacement here, will end up being related to this overlap factor of just R and the vacuum on the output modes. And then whatever's going on with this kind of Hamiltonian coupling in the meantime. And if I work this out carefully, I can write this in the form of what looks like an effective Hamiltonian evolution times this overlap factor. And this effective Hamiltonian has the following structure. It has the structure of the usual resonator evolution, and then it has two non-Hermitian terms that appear in it. The first term here depends on R. So this is a stochastic R that'll be randomly measured, and this is going to induce the measurement back action on the resonator due to me measuring the resonator. The other term here appears at second order in evolution, and this is actually the same term you would expect from the Lindblad formalism for a no jump type of resonator decay. And what this is just saying is that the resonator photon number decays steadily at some kappa, rate kappa over 2. Now, this important term here that depends on R is a stochastic measurement back action. And what's interesting is that this basically follows from this kind of expression, more fundamentally like in the middle of the derivation. And this expression is a complex weak value of the resonator coupling to the output transmission line. So what we're seeing here is the relevant part of the stochastic non-Hermitian Hamiltonian evolution of the resonator is actually of the form of a complex weak value of the coupling between the resonator and the output, pre-selected on kind of what you're inputting and post-selected on the specific thing that you're measuring. Which again is very intuitive that it has to be this form, that I get a complex weak valued dynamics that appear here, where the stochasticity of the dynamics is because each post selection is random. So the specific R for each unit time is randomly being kicked around, which means per unit time I get different randomly chosen weak valued evolutions for that particular time segment of the resonator. Now I know I'm running low on time, but we did another check, is this the right form of what we expect? Because there's a lot of stuff going on there at the more rigorous level. We showed from a different approach that we can constrain it must be of this form by looking at the Husimi Q distribution and saying that, well, I know if I have a coherent state in the resonator, I know the Husimi Q function has this nice complex Gaussian form. That by definition must be this kind of sandwich of the POVM, the actual POVM that I need. So then I know that whatever the total POVM is now going to be some integral over all of these things. So I can use that, factor it, figure out what the POVM is directly from this kind of assumption. And then I find that indeed, when I just factor the POVM with minimal constraints, I get exactly the same kind of structure. So the same stochastic kind of non-Hermitian Hamiltonian appears, the same kind of Lindblad-like term, non-Hermitian decay term appears. So I'm pretty sure this is right. From two different derivations, I get the same thing. And the question is, does it actually work? So to make sure this worked, I had an undergraduate, in this case, Corey Pantea, code this up in Python and make sure that yes, indeed, we get the right dynamics for the joint qubit resonator entangled state. And this is something that really hasn't been that well explored. So in the simplest case of weak measurements, we see indeed qubit that is just orbiting with some Rabi evolution. In the weak measurement case, looks like basically unperturbed Rabi evolution along some axis aligned with what I expect. But even in the weak measurement case, and now I have access to the conditioned coherent states in the resonator, which are these A0 and A1 here. And what you find is that the mean of the conditioned A in each of the resonator actually has these nice kind of spikes in it, which are indicative of the weak valued nature of what's going on in the resonator. So we can see this even in the weak measurement case, the structure is indeed there in the resonator, which is nice to see. More interestingly, as I start ramping up the measurement strength, then I'm going to get to a frustrated regime where the measurement and the unitary dynamics are kind of comparable, in which case nothing settles down, everything looks kind of a bit messy, and I don't get any clear steady state type behavior out of it. But if I keep ramping up the measurement strength, then I get to this wimpy measurement regime where now the measurement's strong enough to start kind of pinning me towards some measurement poles, but indeed I see a rotation of my measurement axis. So now I'm reproducing what we saw experimentally that by having a rotating qubit while I'm simultaneously measuring, it does in fact rotate the measurement poles, and this model correctly reproduces that experimental feature. And notice here, I'm also starting the resonator in vacuum and ringing up the resonator. So it's very much a non-transient simulation, non-transient evolution. It eventually gets up to a steady state, but even at steady state, I get these tilted measurement axes, which is very nice to see. Now, if I bring up the measurement strength even more, then eventually the measurement dominates the unitary evolution and it rotates back to the original measurement poles, and I get very nicely pinned on a Zeno effect. But because I'm bringing it up again from zero, you can see this pass through all of these different regimes kind of very rapidly during ring up until it gets to this nice Zeno pinned regime at some particular time. So sorry for going a little bit over here, but had very nice questions along the way. But the main takeaway here is that superconducting qubits naturally use these continuous measurements, which have a whole lot more information in them than a typical projective measurement. And it's a very rich theoretical structure and quite complicated. But there are various levels of approximation we can use to get effective measurement models, depending on what regimes you're planning to work in. But I think this is very interesting behavior to explore in these transient regimes, in these low probability regimes, like these weak valued dynamics. That requires this more detailed, comprehensive model to make sense of. And now that we have kind of a better understanding of this, I'm expecting to see a whole lot more interesting results about those exotic regimes start forthcoming. So thank you for listening to my long spiel.
Questions? Kai is a red light.
Are Wimpy measurements also a standard quantum optics thing?
No, wimpy measurements are definitely a me thing. In fact, we had a lot of debates about the names of these regimes because strong and weak are well established. We eventually settled on wishy-washy for this kind of competition case because you can't really say very much. They're competing so much, say much. But wimpy is good because it's not quite strong enough to totally dominate the unitary dynamics, but it's strong enough to get Zeno-like behavior where I'm being pinned to different eigenstates. This, if you like, hybridized eigenstates.
More question from the local audience?
I see Gleb was a hand
Yeah, we
up.
have time. So Gleb, we have a question from Zoom. Go
Yeah.
ahead, Gleb.
Yeah, hello. I have two questions. One question, you mentioned that the dynamics of a qubit cannot be arbitrarily fast. And on the other hand, all the dynamics of this composite system is tied to transmission lines because of leakages. And my impression is that these transmission lines, their role in this composite dynamics is that they slow down the qubit dynamic. Do you have some special restrictions on qubit dynamics due to transmission, the presence of transmission line? And second one is about weak values, where do you have also any special restrictions or conditions which determine when you can replace your true Hamiltonian by the effective Hamiltonian with a weak value, meaning that the evolution in that case looks like one being driven by weak values. And the question is whether it's always the case or there are some restrictions on that. So that's...
Yeah, good questions. So the first question, if I remember right, is are there restrictions on the qubit evolution and the speed of it? And the answer is not fundamentally. When I was talking about restrictions, I was saying in the steady state model, then I have to make certain assumptions about the qubit evolution not being too fast compared to these little boxes dt that I'm decomposing into. As long as qubit evolution is slow compared to that, then the steady state model works really well. But if the qubit evolution starts getting faster, then I'm going to get transient hybridization between the qubit and the resonator. That transient hybridization is precisely what produces these kinds of tilting effects that I was talking about. So the point of going into this like more detailed model here is that we can lift these assumptions about the qubit dynamics and still be able to discuss these transient effects. And indeed, we see that we do recover these kind of tilts, like here. The tilt is reproduced. So we are getting this correctly. Now, what we can say is that if your qubit evolution is too fast, like suppose I have a Rabi drive on the qubit evolution that's 1,000 times faster than this resonator decay. What's going to happen is that the resonator, the photons entering the resonator, they linger in the resonator for a time of about 1/kappa, crudely. And in that time, if the qubit is like spinning around a whole bunch of times, then the effective resonator information or effective information imprinted on the resonator state over a time of 1/kappa will average over the qubit dynamics. And so you're going to effectively get the entire evolution of the qubit kind of rotated out, which means that the net like averaged resonator state that leaks out in this time 1/kappa will then have kind of no information about the qubit state because it's been averaged over all the dynamics. So too fast qubit dynamics, actually the resonator becomes insensitive to learning any information about that qubit. So we kind of want the qubit or the resonator dynamical rate to be much, much faster than the qubit rate, typically, just so it's sensitive to the qubit information on timescales relevant to the qubit dynamics. But there's no fundamental limitation for that. It just means that we will get a crappier readout if our qubit's moving too fast. So that's your first question. And give me a reminder of your second question.
Yeah, the second one is about weak values,
Yes,
weak value dynamics.
Yes, this is a very good question. So if I go back to this slide, there's something very important here. Like if you look at this very first line, or maybe the second line here, notice that you have the propagator pre and post selected on specific output fields. So this is actually the correct formulation of the cross operator. This is accurate. But if I want to think about it as an effective Hamiltonian, then what I have to do in order to make it look like a weak valued Hamiltonian is I have to expand out this propagator to like linear order in delta t and then repackage it back into an effective Hamiltonian, which means that I'm neglecting higher order terms of this like total cross operator MR here. So to answer your question, there will be higher order terms if your delta t is bigger, but this formalism doesn't actually prevent you from doing that. It just means this approximation I'm using to think about it as an effective non-Hermitian Hamiltonian evolution breaks down if this delta t is too big. Basically, it's not the same Hamiltonian for that entire delta t. But as long as I have a very, very short delta t, all the dynamics are slow compared to that delta t, then I can do this kind of linearized approximation and think of it as effectively a non-Hermitian Hamiltonian. But the main point is that the cross operator is still a pre and post selected propagator, if you like.
Meaning that you can make delta t arbitrarily small to make this work. Yeah,
so I can imagine a detector that has just a very broad bandwidth, and I can get a very, very narrow delta t resolution, and this will get more and more and more precisely conforming to this non-Hermitian Hamiltonian. But of course, an actual like finite delta t in the lab, I have to be careful about this full expansion here, whether or not that will be accurate.
But in this case, do you deal with ensemble of equal quantum systems or particles, or it's sequential events? Just because I addressed this question about the validity of weak valued Hamiltonian several years ago, and I came up to, so I call this like weak quantum evolution, the evolution which governed by weak values, and then the weak values can be an outcome. So, and I found the restriction. So if you have very big ensemble, the size of ensemble makes higher order terms relevant. Meaning,
yeah, in this case, there's no ensemble. I've been assuming efficient measurement for sake of simplicity here. So this is a single realization, meaning I have one experiment and I have a sequence of things happening in that one experiment to the same system. There's no ensemble. This means that per unit time, each different delta t, I'm going to get a different R, different result that appears on my oscilloscope for that delta t in that one realization, that one experiment. And that means for every delta t, I'm going to get a different weak value here, different effective Hamiltonian that kicks my system around in a slightly different way. And that's going to be a stochastic effective Hamiltonian that conforms to this weak value on that single realization. So there's no ensemble here. And it's very important there's no ensemble here. Now, if I have loss, what happens with loss is that to get the effective dynamics, I need to average over all the things I didn't see. So then I have to introduce kind of the ensemble of things I didn't actually collect as a signal. And then I'm going to introduce at least a partial ensemble to my description. But at this level, I've carefully said, let's assume zero loss just to see fundamentally what's going on. And then we can easily introduce loss to more realistically model finite quantum efficiency and so forth. But at this level, there is no ensemble. It's a single realization, and it's a sequence of measurements made on the same system.
I see. So, and this situation where all dynamics is reduced to bosonic modes, can it be put like that, that you can effectively get rid of a qubit dynamics? So all quantum dynamics can be say considered via these bosonic modes, like you can exclude, for example, qubit variables from your equations.
Well, not really. So actually, this is related to a very important point I didn't quite emphasize, which is that the final structure that I have here of these measurement operators only depends on the resonator. So notice in this effective Hamiltonian, the stochastic term only has A in it. It doesn't have a qubit variable. And I think this is what you're pointing out. This is very important because what this is saying is that what I'm actually measuring is what leaks out of the resonator. So the main impact that I have of measuring my transmission line is to collapse the resonator in part. But the resonator has coupled dynamics with the qubit. So notice there's this chi sigma z term still in the Hamiltonian right here. That's generating entanglement between the qubit and the resonator. So even though I'm like manipulating the resonator with the stochastic collapse back action, it actually affects the qubit indirectly through the entanglement with the resonator. So if I didn't have this qubit term, then I wouldn't have anything that would resemble measuring a qubit because my qubit's not in the problem. That qubit is an essential component of this, but the measurement process itself only depends on the resonator. This is actually what I wanted to see when I was deriving this, because what we want to do is kind of swap out this simple two-level dispersive model for the qubit and put in a more complicated circuit like a fluxonium with arbitrary coupling. I don't have to change anything about this measurement operator structure because all it depends on is the resonator, which means now I have a universal measurement model for this continuous system that can now apply to any quantum circuit I want to couple to such a dispersive readout or such a resonator coupled model. So the answer is no, you need the qubit if you claim that you're measuring a qubit, but the readout process itself doesn't depend on it being a particular qubit now.
It looks like the cavity is a part of your quantum detector,
And this is actually why I like this problem, is because it puts into sharp relief exactly what you're talking about, because this is the actual physical setup. And you say, what is the detector here? In terms of how does the math correspond to the detector? It's the cavity, yes, but it's actually the entire transmission line is what we're using as the detector here, including how we pre-select the transmission line and post-select the transmission line, how we apply the boundary condition at the transmission line, and what the propagator is per unit time. So this cross operator kind of tells us what is the structure that's relevant for the detector, because it has the pre-selection, post-selection, and has what the interaction is, it has which modes are relevant in that interaction. So it just tells us what the detector is on this kind of system. And that I like to see, because otherwise there's a lot of debate, like what do you consider the detector? This is what the math says the detector is, the effective detector that's relevant to getting the effective dynamics. This is what we mean by a detector.
It looks like if you take, for example, charge qubit and quantum detector for it in the form of quantum point contact, then you can consider this quantum point contact via bosonized fermionic operators, via bosonization. Then it looks like in the Latinger liquid paradigm or something like that. So in such the case, the model should be similar to this in principle, because in both cases you have qubit, you have bosons, bosonic modes, which in one case the leakage mode propagate, but in quantum point contact they just time dependent, and here you have also the propagation in space, it seems.
Yeah, and it's a good point, because Sasha Korotkov actually started out his analysis of continuous measurements using quantum point contacts originally in solid state. And so at least a lot of the steady state type formalism, where you're conditioning on a particular current, does work, but he never formulated the point contacts in terms of coherent states because they're not bosonic. You might be right that with a Letinger liquid type model, you can bosonize it and get a similar model out. I haven't thought about this yet. That'd be interesting to see if it works out the same way.
I made a paper about that. Actually, two papers. One paper with my collaborators in Berlin in 2017 about Latinger liquid ideology of quantum detection for charge qubits. This can be relevant just because in practice this quantum point contact can have effectively one-dimensional leads. These are quantum wires. If you have one-dimensional quantum wires, the effective description is via Latinger liquid, so it can be relevant. And second paper is my paper in 2018, just the development of a previous ideology, considering some effects in due to bosons, due to Latinger liquid, and I can, in principle, I can send maybe to you.
Yeah, you should send me these papers. I'd be interested to see, because you may be right that in those approximations, these 1D wire approximations, maybe a lot of this formalism that we're using for circuit QED can port over to the quantum point contact world, which
I'm not claiming that the model is very similar. So I understand that there are details and subtleties which are different, but maybe main physical effects or main features can be similar in these two approaches.
I appreciate the pointers. Thank you for the questions.
Yeah, thank you for your comment.
Yeah, I think we can stop here, and thanks Justin again. So thank you. Thank you everyone for turning up. Thanks for the questions. Next week we'll have Marco, right? And then the subsequent week we'll have Alex Wills zooming in. And I'm already accepting names for next semester. So please send some names, some suggestion, and I'm gonna abandon some liberal tendencies that I have inside me and use other tendencies. And if I don't have names, I will start volunteering people especially students, to present next semester. So yeah, bring me beer. And what? And who is the deputy director of the IQS in Andrew's absence? So should we take Justin for lunch then?
The problem is that if we only have internal people, then they won't reimburse it.
Oh,
We should
really?
take Justin for lunch, but I can't guarantee that if somebody puts it on the P card that it'll be.
So then no free lunch today, I suppose.
I mean, we can go for lunch, but it's like I don't know.
So thanks, Marlena.